So there are two folded cascade topologies. So let me just draw it anyway. One of them was to use a PMOS cascade like this. Okay. And then here we have the active load. And this is a current source. Okay. And the other topology that we started off with was to mirror currents using this. The current mirrors are cascaded. These are the current mirrors. This and this. They are cascaded by these two transistors. And then you again have the active load. Okay. So the part because of the active load is the same. So what do you think is the difference? What happens at high frequencies because of this node, this particular node? So there will be a parasitic pole. What is the frequency of the parasitic pole? I think this was M7, M8. What is the conductance associated with this node that gives you the pole? GM7, right? It's a common gate amplifier, so it will be GM7. And what is the total capacitance here? So there is, So there is CGS of this transistor and the drain capacitance of this transistor, the drain capacitance of this transistor, and the source capacitance of M7. Okay. Okay, that's the order of magnitude of the pole. What is it in this case? What happens to the frequency response in this case? First of all, you have the parasitic pole here, okay, at this, because of this low pass filter. Current going from M9 through M7, part of it is get shunted through the parasitic capacitance, okay. So there will be a pole GM7 by CGS7 plus CSB7 plus CDB9. Okay. What else? Is there something extra here? we have an additional pole here because of the current mirror, okay? Because all of this current will not get reflected in M9. It's not the same current that is folded, it's low pass filtered again, okay? What is the frequency of that pole? The pole here? Yeah, so we have GM11 by 2 times. So first of all, let's assume that this and this have the same size. So they mirror the same current. In that case, it is 2 CGS9 plus CDB1 plus CDB11 or CDB9. Okay. So you have an extra pole, and the combined effect of the two poles, if we use this reciprocal addition, okay, what do we get? We get something that is lower frequency than this. Okay, we can expect it to be lower frequency than this one. Because, first of all, what is the size of M9 here compared to here? We don't know. I mean, we can design it for differently, but this is M9 in the left topology is carrying twice the current of this one. Okay. So we just say that M9 itself is twice as large. Okay. So I'll call this, if I indicate all of these by prime, this CDV9 will be 2 times CDV9 prime, but everything else will be the same. Okay. Whereas here you have pretty much all of the same quantities. Okay. So you have 2 poles one after another, and you will get a poorer frequency response from this topology. Okay. So that's the difference. So generally this mirroring it will have poorer frequency response. Initially it was used sometimes. I mean, the idea was that you don't have to use a 1-to-1 current mirror. Okay. If you use a 1-to-n current mirror, what happens? What quantities change? Everything. No, DC gain won't change actually. DC gain will probably remain the same if you simply scale up the stages. But you have a certain signal current in the first stage. You multiply it by n times before delivering it to the load. Okay. So the unity gain frequency increases by a factor of n. But of course, you are also consuming n times more current. It's not like you are getting something for free. Okay. So you can scale up the GM of the first stage by having a current multiplier. So that, but overall, if you design this one for the same overall GM, I think you are still doing better off by doing the folded cascode like this. Folded cascode like the first one. Okay. Oh, what I have is the GM of the first stage, and then I have a current amplifier, right? What is the GM of this overall? Okay. If I have VD here, I get n times GM times VD at the output. Anything else? The bottom line is you are driving the CGS of those transistors, whereas in the other case CGS doesn't appear in the picture. Okay, and you have the extra pole. So the first topology where you fold it at the source tends to be better than mirroring the current. Anything else? So let's say now we have a resistive load in addition to a capacitive load. Okay, and this side is connected to incremental ground. I mean, it has the correct V bias. Certain load conductance and certain load capacitance. Okay. What happens if we drive it with the op amps that we have designed so far? What is the DC gain? GM1 by G out 1, whatever the G out is. So, plus GL. Now, for a differential pair, G out 1 is GDS1 plus GDS3. Okay. And for a cascode amplifier, it is something smaller than this. Okay. It is this divided by some GM by GDS ratio. Even then, I mean, if GL is the dominant term, the DC gain doesn't change. So, it doesn't matter if you use a cascode or a regular differential pair, the gain will be roughly GM1 by GL. Okay. So, this is something you can't get by using a cascode, because the cascode only increases the output resistance of the current source, but it's still a current source. Okay. So, you only get the transconductance divided by load conductance to be the DC gain. So, this is not a very good way of doing it, and the only way to get a large DC gain is to make GM1 much more than GL. But then your current consumption will increase enormously, right? Because if you simply increase the current, then the GM is proportional to the square root of the current. If you increase both current and the size, you can make it proportional to the current. Even then, I mean, if you want to go from a DC gain of 10 to 100, you have to increase it by factor of 10. Okay. Whereas by doing a cascode, you really didn't increase the current consumption at all. You just increase the DC gain. Okay. So, if I am only interested in the DC gain, what do I do? Huh? So, I can put a voltage controlled voltage source, which is what? Like what kind of stage is it? Source follower. So, I can use a source follower. So, let us try to do that. So, this is, let us assume that the first stage is a differential pair. Okay. It doesn't matter which one it is. You can use the differential pair, folded cascode, telescopic cascode, anything you want. And this is biased at a certain current. Okay. And the load is connected to it. What will be the DC gain of this stage? Approximately, what's the DC gain? It's the DC gain of the first stage, right? Let's assume that this is indeed behaving like a voltage buffer, then it's the DC gain of the first stage. We know that, of course, this one won't behave like an ideal buffer. It will have some output resistance. So, DC gain will be smaller than that, but it will still be close to the DC gain of the first stage. Okay. What is the potential problem with this? Okay. What else? What is the swing limit of this? First of all, this GM1, the input stage, we can use it with a PMOS input pair or an NMOS input pair. Okay. Which one will we use? PMOS. Why?
Because in the PMOS, we can have for the PMOS, we can have the output convert to the lower head.
Yeah. So, see, for an NMOS, with an NMOS input, the output range goes from some VDD. I am assuming a simple differential pair now, not a cascaded one. Okay, this is the upper limit, and the lower limit is something. It is the input common mode minus VT. Okay. So, it is closer to, if you think of the range 0 to VDD, it is somewhere here on the upper side. Okay. For NMOS, correspondingly for PMOS, it will be near the lower side. Okay. So, which one do we want? The one closer to the upper side, right? So, what is the output swing limit of this? the whole thing minus Vt. If we assume no body effect, the entire swing limit gets translated by Vt, isn't it? I mean, sorry, not Vt, Vt plus Vd sat, VGS of the source follower. So it will be something like this. So this kind of thing is okay. Now what happens with body effects? Yeah, there will be some nonlinearity. So upper threshold will fall more. Yeah. So the swing limit will reduce even more. Okay. So it may be something like this. With this is at the source follower output, and this is at with body effect. Okay. The VGS of the source follower increases as the output voltage increases. So at the upper side, it will have a much larger drop. So the swing reduces even more. Okay. So the bottom line is the swing that you can get by driving a source follower from a differential pair is rather small. Okay. PMOS instead of NMOS. Okay. So that's what will happen then. Can you use it? Yeah. How will that work? That will not even work, right? Because the output of the PMOS varies in this range, the first stage, this part of it. Then use PMOS source follower. Yeah, what's the difference then? Only thing is the body effect will be gone, that's all. Okay. Still it is a small range that is limited to the output range of the voltage follower. Output range of the differential pair. Okay. If you use a folded cascode which has a larger output range, it still doesn't help. Then it will get limited by the source follower. Okay. Because as this voltage comes down further, what is the lowest voltage we can have at this point? So it's the VD sat of this plus VGS of this. Okay. So the bottom line is, what is the upper limit on the output voltage of the source follower? It's, of course, the previous stage also has to operate. So it will need at least one VD sat. Okay. So this will be, the upper limit will be something like VDD minus VD sat minus VGS. Okay. VGS 11. And the lower limit will be VD sat. So in a low voltage technology, this is not a great thing. What are typical values? Let's say VD sat is 0.15 for everything. So what is this? I mean, VT is 0.6 or so. Okay. So this is some 0.9 volts or 1 volts or something. And the lower limit is 0.15 volts. So we have lost more than half of the 0 to 1.8 volt supply. Okay. That's why this is not favorable. You could have used this when you had high voltages, but now this is not a good thing to build. This is okay. So generally you avoid source followers when you have swing constraints. You can use it, it is used in some cases. So whether it's PMOS or NMOS, it doesn't matter. Of course, with the NMOS you have the extra complication of the body effect. But with PMOS, if you choose to tie the bulk to the source, then it will introduce a large output capacitance. Okay. So we don't want to use a source follower. What else can we do? A common source amplifier, right? So the second stage also has to be a common source amplifier. So the source follower is fine, it will give you a relatively low output resistance, but the problem is swing. Okay. Now, we want to have a larger swing, so then we will use a common source amplifier. That's the only amplifier we know which gives us a large swing. Okay. So let me start off with the differential pair that we know so well now. Okay. What is the quiescent output in absence of mismatch? Here? VDD minus VGS 3. Okay. Now I want to use a source follower, common source amplifier here. Will I use a PMOS or an NMOS common source amplifier? PMOS. Why? So this is closer to VDD, and also this voltage is some fixed value, okay, depending on the VGS of M3. So I can try to use an NMOS like this. Then the current through the NMOS transistor depends on VDD also, right? As I change VDD, it will change. That's not a very good thing to have, because this voltage is at VDD minus VGS 3. Okay. So I'll use a PMOS. What is the VGS of this PMOS transistor? It is VGS 3, right? So this is a case where we don't have to do anything, meaning the previous stage provides the right VGS. So then you adjust the size of this, let me call this M11. You adjust the size of M11 to give you the correct value of bias current with the input voltage that it has. Okay. Okay, whatever quiescent current you decide, we'll later see how much that should be. Now, how do I get the signal out of this? This M11 has a quiescent current. M11 has a quiescent current I1, and it has some signal current. Okay, that depends on the signal swing at the input. I want to get only the signal current out. What do? I just subtract the bias current. Okay. So I can have a current source of I1. Now it can also be biased from the same VGS as this, and it could also be biased from a separate current mirror. It doesn't matter. For now I will draw it as though it is biased from the same current mirror. So this is M12, and M12 is sized so that with the value of bias you have here, it will give you a current I1. Okay. So both sides are adjusted so that in absence of mismatches, etc., you will have a current I1 and only the signal current flows out. Of course, this does not mean that you can operate the op amp in open loop and expect it to work. You will always have random mismatches which will take the output to either VDD or ground. Any questions? Yeah, so this will, like I said, this will work properly only when you put it in feedback. In absence of mismatches, we can do the analysis. Okay, the point he raised is that we have two current sources feeding into each other. Okay, so what will happen then? First of all, I have not connected the load yet. And this is connected to some bias. Let's for now assume that it has the correct value to keep the transistors in saturation. Let's not worry about exactly how much it is. So what happens if there is a current imbalance? The problem with what is the problem with having circuit like this? You can't easily determine the output voltage. It's a very high impedance node. So small current imbalances will make a large change in the output voltage. Okay. So that's why you can't have that working in open loop. But of course, you can have it working in closed loop. Okay. In fact, this high impedance is what gives you the high gain. Okay. So you will have structures like this in the amplifier. For instance, here also. M2 is a current source, M4 is another current source, and they are connected together. And if you try to make this in open loop, it will not work. But once you put it in closed loop, it will get the correct value of bias. Okay. So similarly here, in this case, if there is an imbalance in current between M11 and M12, it will flow into GL and cause this voltage to be slightly different from Vout bias. Okay. Let's assume that is of the value so that all transistors are still in saturation. Okay. I mean, this is why you can't use op amps in open loop or in general any high gain systems. A small offset will take you to the saturation levels. Okay. So fine, we have some structure now where we have the stage that we knew before, the differential pair, followed by the common source amplifier. Okay. So this again we had discussed earlier. If we want to drive a resistive load, it's better to drive it with two stages. The first stage which is not loaded by a resistor, and the second stage which is loaded by the resistor. What is the DC gain of this? What's the DC gain of this stage? Actually, let's even before that, which is the plus and which is the minus terminal of the op amp? Before we had this to be plus and this to be minus, and this was the output. Okay. Now from here to here there is an inversion because it's a common source amplifier. So okay, and this is the output. So I bias this at some VCM plus VD by 2, then VCM minus VD by 2. What's the result? What is the DC gain of the circuit? What's that? Yeah, this is a cascade of two stages, right? From the input VD to this point, we have the gain of the differential pair, and from here to here, we have the gain of the common source amplifier M11. Okay? So the DC gain will be this part, which is the DC gain of the differential pair. And what's the DC gain of the rest of it? JM11 by? So it's a GDS of both of these, this transistor, and any load that you connect. Okay? In case your load conductance is dominant, your load resistance is rather heavy, GL is much more than GDS11 and GDS12, and you can approximate it to GM11 by GL. Okay. So this type of topology is used both for capacitive loads in some cases and also with resistive loads. Okay. If you have a heavy resistive load, you can neglect the GDS of M11 and M12. So fine, the DC gain is certainly higher, and also it's not very sensitive to GL. Okay, if we drove GL with a, let's say, folded cascode amplifier, then the gain is approximately inversely proportional to GL. Okay, now, well, here also it is, but the first stage gives you a high gain. You can design the first stage to give you whatever gain, and the gain of the first stage is not affected by GL. Okay. So you don't have to make any of the GMs 100 times the load conductance to get you a gain of 100. What do you do if you want a gain of 100 here? What would you do? Like, what's a sensible strategy to use? So maybe you use use 20 here and then 5 here or something. Okay. Then you have to make GM11 only 5 times GL, and you put all of the gain here. You can even go further. You can make 50 and 2 or something like that. Okay. So you can let the second stage have a relatively low gain, which means that it needs a small GM for transistor M11. But you can have the first stage have a large DC gain. Okay? Because the first stage gain is not affected by the load resistance. So fine, am I done here? So this is the op-amp that's complete. So what is the frequency response of this op-amp? Where are the poles of this op-amp? Let's neglect CGD as usual. Where are the poles of the op-amp? How many poles and zeros does it have? So first of all, again, it's a cascade of two stages, right? What were the poles in the differential pair? We had the output pole, which is a ratio of GDS4 and GDS2. GDS4 plus GDS2 by the load capacitance that you see here. Okay? And you had the mirror pole and 0. And what happens here because of the second stage? We'll have one more pole because of GL, GDS11, GDS12 and CL. Okay? We'll have pole set. What is the load capacitance of the first stage? CGS11 and also capacitance of M2 and M4. Okay. And what's the pole because of the output? Okay. And what else? What other poles do we have? Current mirror. So what is that? And there will be a 0. Okay. So now, what is the problem? Is there a problem, or can we just use the op-amp as it is? Yeah, that's correct. We have to ensure that there is 20 dB per decade roll off. Now, the problem here is that P1 and P2 can be close to each other. Okay, relatively. Now, that depends on the relative values of GL and also the value of CL. Okay, the conductance here is larger, but also there can be a large load capacitance. So, it is quite possible that P1 and P2 are close to each other. So, will we have 20 dB per decade roll off in that case? No. Okay. So this is equivalent to, I think we have seen these two poles before, right? If you have, let's assume a transistor without CGD, you drive it with some source resistance and you have some capacitance at the output. So the input pole is related to RS and the capacitance you see here. Of course, there is some additional stuff here also because of the previous stage. And the output pole is related to the output conductance and the capacitance that you see at the output. Okay? And the two can be comparable. There is no guarantee that one will be much smaller than the other one. So we need to do something more in order to enable us to use it in a feedback loop. Okay? So what can we do? What happened with the single stage op-amp? How did we get the first order roll off? No, with the single stage differential pair. So we had some load capacitance and we designed the GM to be appropriate for it and made sure that all the parasitic poles and zeros were beyond the unity gain frequency. Okay. So essentially, if you have a large capacitor from here, then certainly it will compensate it. Okay? Meaning if I add another capacitance here, make it large enough, then certainly P1 will go low enough that all the other poles will be beyond the unity gain frequency. Okay? So that's one way to do it. Or I can do it to this one. Okay? I can do it to one of these two. Right? I can always make P2 much smaller than P1 also by hanging a large enough capacitor. But is that what I want to do? What's the problem with this? So it will compensate it, no doubt. You can make it stable. You can make any circuit stable by hanging a large enough capacitor from some particular node. Okay? But what is the unity gain frequency you will get? That's the problem. Okay? You will reduce the bandwidth to very low values. Obviously, let's say I choose to do this. Okay? What will be the unity gain frequency? What's the limit on the unity gain frequency? So let's say I choose to just make P1 to very low frequency. What is the limit on the unity gain frequency I can get? Huh? No, but what is the limit? What is the ultimate limit? How can I evaluate the limit? I have to make Cx large enough for it to be stable. So what is the unity gain frequency I am going to get at that point? That depends on other poles, right? If you don't have any other poles, I don't care about making it very large, making Cx very large. So roughly, yeah, P2 by 2. Maybe I will say that the parasitic pole has to be twice the unity gain frequency or 1.5 times. Whatever it is, it has to be beyond. So I have to make Cx large enough so that the resulting unity gain frequency will be below P2. Okay? So P2 is in fact the limit on the unity gain frequency. Similarly, if I choose to make this lower, what is the limit? P1, obviously, right? Now, if you look at it, so P1 or P2 will become the limit on the unity gain frequency. What was the unity gain frequency of the single stage amplifier? GM1 by CL. Okay. So if you compare it to this quantity, P2 and P1, are they lower or higher? Lower, right? P1 definitely, because it's a ratio of some GDS to some capacitances, you expect it to be lower. Okay. And similarly, P2, it is not just GDS, it also has GL, but again, it is GL versus GM here. Okay. You can expect it to be lower. So it looks like you are sacrificing a lot in unity gain frequency. So what do we do now? I think we already know the solution. We have discussed the common source amplifier endlessly before. Huh? How will we do that? Yeah. So that's not by creating a zero, right? We are doing pole splitting. Okay? Because that zero is in the right half plane. It in fact worsens stability. Right? It doesn't enhance stability. So if you try to hang a large capacitance from either of these two nodes, you can compensate the amplifier, but to a very low bandwidth. Okay? So the better thing to do is, initially these two, the pole at the input of M11 and output of M11 will be of the same order. I mean roughly similar values. Now we saw that if we use a capacitance Cc, or if somehow the CGD of the transistor M11 became very large, what does it do? It splits the poles. You still get two poles, but one of the poles moves to lower frequencies than before, the other pole moves to higher frequencies than before. Okay? So this is a better compromise, it looks like. Right? Because now the pole that moves to lower frequencies is the dominant pole, but the other pole has been moving to higher frequencies. So the limit on the unity gain frequency is higher. Okay? So this is clearly a better method of compensation. So this can be done, but results in a low bandwidth. So this is known as Miller compensation. You use Miller compensation by using a capacitor across the gate and drain of M11. This gives you pole splitting. Okay. What is the resultant frequency response? So, but what are the poles and zeros? P1 will be dominant pole. So, the pole associated with the conductance here moves to low frequencies. The pole associated with the conductance here moves to high frequencies. So, what are the values of the poles? Do you remember? So, one thing is we saw that the pole associated with the input side is close to the conductance you see here, which is still GDS3 plus GDS1 divided by the total capacitance, which is all of the parasitics here plus the Miller multiplication of Cc. Okay? That is approximately the value of the pole. What about the output side? What was it? This is exactly like the problem considered in the first assignment, as usual. You have a current source with some resistance driving a common source amplifier. Okay? This current source is the first stage transconductance, and the resistance is the total output resistance of the first stage. Now, we not only have CGS of this, but we also have the output capacitance of the first stage, which can be absorbed into CGS. And we have CC, which is like CGD. Okay? And we also have some resistance and capacitance from the output. Okay? What are the two poles? The pole on the input side is 1 over Rs times the total capacitance you see, which includes the Miller multiplied Cc. What about the output side? What was the pole? GM will increase. Yeah. So it's now this is in a feedback loop. Okay. So the conductance looking into the transistor will be GDS, of course, plus this capacitive division ratio times GM. Okay. That's the total conductance you see, plus GL is connected to the output. That also appears in the expression for the pole. And what's the total capacitance? It's the CL and the series combination of these two. Okay. So if this is not very clear, go and revise the stuff on the common source amplifier. We have discussed all of this before. Okay. Okay, it's the sum of this. This is the total denominator. Okay. Plus GL, yeah, thanks. Maybe I should write this on a different page altogether. Okay, where Cp is the total parasitic capacitance you see, and it is equal to this. What's that? Oh, it's just GDS 11 plus GDS 12. Okay. What happens to P3? What happens to this P3? Remains the same. And the 0 remains the same. This happens inside the differential pair. Okay, before the second stage is driven. So P3 and Z1 will remain the same. Okay. So we have moved P1 to lower frequencies and P2 to higher frequencies. So we can compensate it. What is the unity gain frequency? As I mentioned before, the op-amp is usually specified by the unity gain frequency and the higher poles, and the DC gain. Equivalently, you could specify the lower frequency pole, the dominant pole, but that's generally not done because what appears in the expressions when you put the op-amp in feedback is the unity gain frequency. What's the unity gain frequency of this amplifier? Yeah, what is it? Wow, what's that? GM1? GM1 divided by which capacitor? This GM1 divided by this capacitor. Why? Oh, this one. Yeah. Into GM11 by GL. So what is it approximately? Again, we have calculated this before, right? Huh? GM5 CP plus CC. No, what is the... No, it has to be a frequency. What? Which GM? So this amplifier is like this, okay? So now the second stage is also an amplifier. What is the swing, incremental swing at this point? The output swing, approximately, it's the output swing divided by the second stage gain. Okay? So it is, if we assume that to be rather small, if the second stage has a large enough gain, then what is this? This whole thing is an integrator. Okay? You apply a difference VD, GM1 times VD comes out, and because this voltage is rather small, none of it goes into the capacitor. Okay? Hardly any current goes into the capacitor. All of it goes here. Also, because this increment is small, the output voltage is approximately the voltage across the capacitor. Okay? The output voltage is the voltage across the capacitor plus the input voltage. If the input voltage is small, it's just the voltage across the capacitor. Which is what? Approximately GM1 by SCC times VD. Okay? It doesn't have to be very large, right? This is an approximation, of course, but you don't need gains of thousands to do this, make this approximation. So we'll see what the exact expression is soon. So the unity gain frequency is approximately Gm1 by Cc. Now of course in reality, as we pointed out, if the gain is not very large, some current does flow into this capacitor. Okay. And the output voltage is not exactly equal to the voltage across this. So that will give you some error, but this is a very good first approximation to what happens in the differential, what happens in the two-stage op-amp. Okay. In reality, what is it? It's the DC gain times the dominant pole. Okay. That's again another approximation, right? That assumes also that the gain is large. But let's do that. This is the DC gain, right? And this is the dominant pole. Okay. So what happens? This cancels with this. Now, the only part is, the only approximation is because of Cp. Okay. If Cp is small compared to the rest of the terms in the denominator, then this part also cancels out, isn't it? This Cp appears here because of this current. Okay, it's also taking some current. And why do you get this 1 plus? Huh? No, I know, but why would we get it in the, I reasoned out that the output voltage is the voltage across the capacitor plus the input. Okay, the plus that input gives you plus 1. Okay. So it is this, but this factor cancels with this part. Okay. First of all, this is complicated expression, but this is also not exact because the value of the pole was derived from some approximation. Okay. This is Gm1 by Cc. Okay. I reduced the same expression to something times Gm1 by Cc. Now you can see if Cp is very small compared to Cc, if the parasitic capacitance at that node is rather small, then you can make this approximation comfortably. That's not always true. Of course, you don't want to overcompensate it. You don't design a very large Cc just so that this expression is true. Okay. But it is true. Cp can be expected to be smaller than Cc. Maybe not much smaller. And this factor is 1 plus 1 over the DC gain of the second stage. Okay. Is this correct or no? Yeah, I think it's fine. Yeah. What's that? Yeah, Cc introduces 0. That's correct. It will be exactly Gm11 by Cc. Yeah. Yeah, that's correct. But you shouldn't do that. So what he is saying is, first of all, I didn't mention it explicitly, but this, I should add another 0 here, right? Because we get a right half plane 0 because of Cc. And that is at Gm11 divided by Cc. Okay. First of all, let's see if that is what you describe as likely. What he is saying is, if this 0 happens to be lower than Gm1 by Cc, you will have a problem. But that's not likely. We will see that soon. You can't design Gm1 to be smaller, smaller than Gm1. Okay. You can do it, but it will become inefficient. Okay, so this is the unity gain frequency, which is roughly GM1 by Cc. We will continue this tomorrow. We also have a right half plane 0, which is GM11 by Cc. How will we get rid of the 0? We have put a resistor in series and get rid of it. That's also something we frequently do, because we are unnecessarily introducing a right half plane 0 where we already know how to get rid of it. Okay.